Okay, welcome to lecture number 1. Right now we're going to explore more in depth about hybridization. We've already seen this molecule. This is ethene. It's got a carbon-carbon double bond. We already know that these two carbons are sp2 hybridized. What I'm going to do now is draw in detail how those hybrid orbitals overlap to form both sigma bonds and how the unhybridized p orbitals will form a pi bond. And so if we just want to investigate the sigma bonding network that forms the basic skeleton of the molecule, we can start by drawing our two carbons. And if these carbons are sp2 hybridized, that means they have 3 sp2 hybrid orbitals projecting out from them at 120-degree angles. And so, for example, this carbon here will have 3 sp2 orbitals that project out at what should be exactly 120 degrees. The other carbon will have 3 sp2 orbitals that also project out at 120 degrees. Now notice these two sp2 orbitals are projected directly at one another, and that overlap allows for a sigma bond to occur between the two carbon atoms. And these spaces out here are hydrogen atoms, and they don't have hybrid orbitals, they just have their 1s orbitals. But we get overlap between the two, and that forms a sigma bond as well. And so we've got a sigma bond between carbon and hydrogen, another one down here, a sigma bond between the two carbons, and then there's 2 sigma bonds on the other side as well. So that accounts for all 5 sigma bonds in the molecule. Now there's one more bond, and that's the double bond, or half of the double bond represented in the Lewis structure. To represent that, we'll draw it separately down below as to not clutter up this diagram. And so between the two carbons, we know there's a sigma bond here, and I'll represent that just with a line. The pi bond is formed from parallel p orbitals. Each carbon has 1 p orbital that was not hybridized into the hybrid orbitals up here. Notice they're sp2. That means they only included 2 of the p orbitals. So there's one unhybridized p orbital that remains. And so even though there's 2 lobes, those are just the 2 halves of a p orbital. And we can color in one of the phases as we did in class previously. And so these 2 unhybridized p orbitals are what form the pi bond. And we represent that just by showing communication or overlap between the 2 lobes. And so in looking at our Lewis structure, we can say that there are 5 sigma bonds and 1 pi bond in the structure. Now if we extend this to ethyne or acetylene, it's a very similar case. The pi bonding network is much more complicated because there's 2 pi bonds. But for example here, if we just want to draw the hybrid orbitals first, these are our sp hybridized orbitals on carbon. and they're sp because carbon here is associated with 2 pi bonds. And so there's overlap, again, between the s orbital of hydrogen and the sp hybridized orbitals of carbon. There's overlap here to form a sigma bond between the 2 carbons. And so one of the bonds in the triple bond is a sigma bond. The other 2 are pi bonds. If we want to look at the pi bonding network, again, we can start off with a very similar drawing as we did over here with ethene. In this instance, we have 1 pi bond resulting from an unhybridized p orbital. Now, the important thing to remember about p orbitals is that they come at 90 degrees from each other because they represent an axis on a Cartesian coordinate system that's either x, y, or z. And so if this, for example, would be the z direction, then perhaps we would have another p orbital that was unhybridized in, say, the x direction. And so it should be 90 degrees from this, and it would be coming off the board. But we can represent that by drawing it at an angle. And so this is supposed to be here a 90-degree angle between the 2 p orbitals. And so there will be another one over here on this side. And again, we can color in the lobes such that they're parallel to each other and they agree. This one would be out in front of the board, whereas the other orbital would be behind the board. And so this complete diagram for the pi bonding system of ethyne is drawn in. And so if we combine these 2 diagrams into one, it would show you the complete bonding network in great detail. So for ethyne, we've got 1, 2, 3 sigma bonds and 2 pi bonds. And so this was a very much detailed description of the bonding networks in both of these molecules. From here, I just want to provide one more practice example, and we can simply just label the hybridization of each non-hydrogen atom. So if you can, go ahead and pause your screen and try and identify the hybridizations of each atom that's not a hydrogen. Remember, when atoms have a full octet, essentially all you're doing is looking for pi bonds. There will be extreme cases that we might run into where these rules don't apply. But for right now, they'll apply to everything you'll see. And so if we start at this end, this is a carbon, full octet, 4 single bonds. It will be sp3 hybridized. Again, another carbon with 4 single bonds. One of those bonds is to an oxygen, but that doesn't matter. It's still sp3 hybridized. Oxygen only has 2 single bonds, and then it has 2 lone pairs. But it's not involved with any kind of pi bonding, and so it will not be anything but sp3 hybridized. Remember, the hybridization controls the 3-dimensional geometry, so all these sp3 atoms are tetrahedral structures. When we get to this carbon, we've encountered a pi bond. So it has one pi bond associated with it. That means it's going to be sp2 hybridized. In this carbon, it's the same situation. It is associated with one pi bond, so it is sp2 hybridized. We can just fill those in black so we can actually see them. When we get to the end, we see a carbon that is associated with a triple bond. And so this is not an alkyne, it's a triple bond to nitrogen, but that doesn't matter. Because there's two pi bonds, this is a linear geometry here, and so it's actually depicted accurately, and it's sp hybridized. Nitrogen, being associated with a triple bond, is also sp hybridized, even though there's a lone pair there. And so notice here, the geometry is not accurate for anything except these linear atoms. Over here, we would expect 120-degree angles, and that's not how the structure is drawn. It's drawn inaccurately. So we would know in a true three-dimensional structure, these should be proper 120-degree angles associated with these carbons. Over here, we would need to show three-dimensional structure with 109.5-degree angles. So that wraps up what we want to look at with hybridization. What I want to move into for review purposes is some more discussion about formal charge and some circumstances that perhaps we didn't get to in our lecture. Okay, so here's two examples. One has some atoms that we did not really examine for formal charge yet, but the rules are the same. The other is all nitrogens, and we'll get to that next. Go ahead and assign formal charges. Remember, the most important thing to start is knowing which group number your atoms fall in. And so carbon we're very familiar with, that's group 4. Phosphorus is right underneath nitrogen, it's group 5. Sulfur is right underneath oxygen, it's group 6. So the whole column on the periodic table defines the group. For carbon, for all of these carbons, they each have one bond of phosphorus, and then they have 3 hydrogens attached to them. So they each have 4 bonds, and so the carbons are all neutral. For phosphorus, since it's group 5, and the formal charge calculation is the group number minus the number of bonds to that atom minus the number of electrons in lone pairs. In this case, there is no lone pair. And so we end up with a value of 1, which is a positive value. So this phosphorus gets a positive charge in this structure. For sulfur, that's group 6. It only has 1 bond, but it's got 6 electrons around it. So that gives it a value of -1 in this structure. And so you should have the power to assign formal charges to really any atom in the periodic table, not just the ones we discussed, because it's all based on their group number. If we look at nitrogen, nitrogen is group 5, and here's different environments for nitrogens. If we look at this one over here, it's got 3 bonds and 2 electrons. So 5 minus 3 minus 2 is 0, or neutral. Over here, this nitrogen has 4 bonds, a triple bond and a single bond. And so 5 minus 4 minus 0 electrons is a positive 1. And over here, if we look at this nitrogen, It's got a full octet, but there's going to be a big problem. It's group 5, minus 1 bond, minus 6 electrons. That's a negative 2. It is very rare in stable organic structures to observe a charge that's more than just a +1 or a -1. Anytime you observe a charge like that, it indicates a very lack of stability. Now everything has a full octet, and that's a good thing, but we can probably do better with this structure. But this illustrates a time when formally you have to assign a charge that's greater in magnitude than a -1. And that can occur with positives as well. So you have to go with what the structure gives you. How can we make this structure better? Well, let's get into some resonance. We can draw a resonance structure for this, and I encourage you to pause it and try to draw a resonance structure that is better than this one here. To draw a resonance structure, what we want to do is start off by simply just taking the same atoms in the same position they were and connecting them with just single bonds. We cannot create any new single bonds or sigma bonds. Otherwise, that's not a true resonance structure. The same single bond or sigma bond network has to be in place. It's only the extra electrons, the pi bonds or the lone pairs, that can move around. And so we start off with these nitrogens, and then we need to fill in the rest of the electrons. And so perhaps you were able to arrive at this structure. Here, all of the nitrogens have an octet, and you end up with more of a distribution of that negative charge. So instead of being concentrated on one nitrogen where it's very much unstable, it's spread out to 2 different ones. Now this structure might not look that good either because you've got so many charges. But the fact of the matter is there's no way to give every nitrogen a full octet without having multiple charges. And so this really is the best, most representative structure for what's called the azide ion, or N3-. And this is a stable ion. And it's sold as sodium azide, and it's stable in a reagent bottle. So even though the structure looks like it might not be stable, it truly is. And nitrogen can accommodate a formal -1 charge, but it might have trouble with a -2. So this structure is best. If you did try to draw a structure, for example, if you changed the actual geometry of the azide ion and then perhaps created a new sigma bond, even if this could be stable, when we put in all the electrons, it would not be a resonance structure because you've created a new sigma bond. You've changed how the atoms were tied together with their skeletal structure. And for example, if you went in to this particular example and tried to put electrons, you would find that you could not give each nitrogen a full octet, and you would have other problems. But for many reasons, this is not a proper candidate.